we introduce our paper titled Crystalformer Infinitely Connected Attention for Periodic Structure Encoding. Our work is an interdisciplinary study in machine learning and materials science, which is a field to explore new useful materials such as superconductors and battery materials. Materials are represented by crystal structures. They are infinitely repeating periodic arrangements of atoms in 3D space, described by a minimum repeatable pattern called a unit cell. We here focus on the problem of predicting material properties such as formation energy and band gap from a unit cell of a crystal structure via neural networks. Machine learning-based prediction is much faster than DFT calculations and is useful for accelerating material discovery and development processes. Property prediction is usually performed by neural networks that hold state features for the atoms in the unit cell and update them via interatomic message passing layers. For property prediction, it is important that these networks are invariant to input data transformations such as rotation, translation, and periodic boundary shift. Material representation learning has evolved along with advances in machine learning and molecular representation learning. Particularly, graph neural networks, which have increased their popularity since 2015, are now main approaches in molecular and crystal representation learning. Against these mainstreams, a transformer-based, fully connected self-attention network called Graphomer showed its effectiveness for molecules. But whether such dense attention is applicable to crystal structure is still an open question, which we tackle in this study. Okay, let's start with the simple transformer for molecules. We can formulate its self-attention as the evolution of states of the atoms in the structure. We here employ relative position representation instead of absolute ones by encoding spatial distances between atoms as scalar and vector biases. In crystal structures, there are infinitely repeating atoms, so we add interactions with those atoms in translated unit cells. This is done by inserting an infinite summation to add atoms at translated positions, which are then reflected in the position encoding. We call this formulation the infinitely connected attention. To drive attractive formulation, we use position encoding to explicitly decay the attention weights by interatomic distances. This concept is analogous to potential summation that is usually done for energy calculations in physics simulation. We do it in abstract feature space and call it neural potential summation. Although the infinitely connected attention may look complicated, it can be performed similarly to standard self-attention for finite elements by using special forms of position encoding terms. Our method outperforms most of the existing methods in various property prediction tasks, while performing competitively with PotNet, which is the state-of-the-art GNN. Compared to the state-of-the-art GNN and transformer-based method, our method has highest model efficiency and inference speed. Furthermore, our architecture is simple and more closely follows the original transformer encoder, which makes our method suitable as a baseline transformer model in this area. In the paper, we further discuss its possible extensions, such as the incorporation of long-range interactions by using Fourier space attention. Thank you for your watching.